So in our earlier classes, when we dealt with 2D stress state, we have arrived at these relations where we wanted to find out what is a state of stress when we orient or when we rotate our coordinate axis by an angle theta to x dash and y dash. So we have figured it out what are the stress state in an oriented coordinate axis. Similarly, we can represent this in another fashion or another way as sigma 1 dash, sigma 2 dash, and tau 1 dash 2 dash. So it's another way of representation when we consider coordinate axis to be x1 and x2, and we want to find out a stress state in another oriented coordinate axis, let's say x1 dash and x2 dash by an angle theta with respect to our initial coordinate axis. So this is, you can see that these relations are very big, and when we consider 3D stress state, it again becomes cumbersome. So these two ways of representing become sometimes tedious and cumbersome. So there is another elegant way to find out stress state using direction cosines, matrix of direction cosines. So let me define what is a direction cosine first. So I define a direction cosine as Aij is equal to cos of angle between xi dash and xj. Let me define it over again and explain it. So let's say I equal to 1 and j equal to 1, so it becomes a11, which represents cosine of angle between x1 dash and x1. Similarly, if I say a12, which represents a cosine of angle between x1 dash and x2. a21 represents cosine of angle between x2 dash and x1, x2 dash and x1, and a22 represents cosine of angle between x2 dash and x2, x2 dash and x2. So I define my matrix of direction cosines as having these components a11, a12, a21 and a22. Now let's find out the values of this a11, a12, a21 and a22. For that we need what are the angles between x1 dash and x2, x2 and x2 dash. So this angle is pi by 2 minus theta because x1 and x2 are orthogonal, so this angle becomes pi by 2 minus theta, while this angle becomes theta. So now let's find out what are the values of this matrix, what are these values of these components a11, a12, a21 and a22. So I get this matrix which is cos theta. So a11 is a cosine of angle between x1 dash and x1. So this angle is take a cos of it, so it becomes cos of theta. a12 is represent cosine of between x1 dash and x2, x1 dash and x2. So cos of this angle, that is cos of pi by 2 minus theta, that becomes sine theta. And then a22 represents cosine of angle between x2 dash and x2. So x2 dash and x2 is like cos of theta, so I get a cos of theta. So I have got this matrix which I called as a matrix of direction cosines. Now as I mentioned you, there is an elegant way of finding out this sigma 11 dash, sigma 22 dash, tau 12 dash in terms of direction matrix, in terms of direction cosines. So let's do that. So I have this my stress matrix which I have been given, and there is some rotation which I have put, and by which I get this stress state in other coordinate axis. I call it as a dash. So I have a transformation or rotation with theta. So how I get this? So I will get this using this relation a dash is equal to d a d transpose. So it is my matrix of direction cosines, it is my stress matrix or stress tensor, and this is my transpose of d. Okay, so which is nothing but the matrix of direction cosines. So let me write down these equations again, and let me write down this relation uh, so that you can see that A dash is having terms sigma 1 dash 1 dash, sigma 1 dash 2 dash, and sigma 2 dash 2 dash. And I have the matrix of direction cosines which we have found out in our previous slide, and I have my stress matrix over here, and the transpose of matrix transpose of D, which is nothing but the matrix of direction cosines. So let us see whether this represents these relations or not. So let's try to find out for sigma 1 dash 1 dash using this taking the products on this side, right hand side. So let's do it for sigma 1 dash 1 dash to appreciate that we can get the transformation, the transform stress state using when we know the matrix of direction cosine and stress matrix. So let's do that. Let me write it down. So we are solving it for sigma 1 dash 1 dash. Okay. So let's multiply this by this. So I can write it down it as I will write it sigma 1 1 cos theta plus sigma 2 1 sin theta. Then you have minus sigma 1 1 sin theta plus sigma 2 1 cos theta. Then you have sigma 1 2 cos theta plus sigma 2 2 sin theta, close the bracket. Then you have sigma 2 2 cos theta plus 1 2 cos theta, sigma 1 2 cos theta, and sorry, this will be what? And this will be minus sigma 1 2 sin theta plus sigma 2 2 cos theta. So I get this, and I will write down this matrix cos theta minus sin theta, cos theta. Now let me multiply by this. So I just take first product, sigma 1 1 cos square theta plus sigma 2 1 cos theta sin theta plus sigma 1 2 cos theta sin theta plus sigma 2 2 cos square theta. Now you can see here I have this term and I can add this term. So I have sigma 1 1 cos square theta plus I will write this term here sigma 2 2. So this should be sine square theta. Sigma 2 2 sine square theta plus 2 into sigma 2 1 cos theta sin theta. So why I am writing sigma 2 1? Because 2 here, because sigma 1 2 is equal to sigma 2 1, that is what we know. So we can write this. So we get sigma 1 dash as this term. So we have done it for only one term. So you can see correlate here. So we get the one and the same thing, which by multiplying these matrices together. So this is an elegant way of finding out the stress matrix in a transformed or coordinated axis with respect to theta using just direction cosines and taking its transpose. So even though if you look at these relations or this relation, you will not able to tell, if I say this relation, you will not able to tell what exactly it is representing. It is a 2D, 3D or 1D. You cannot say it from this. Similarly, writing these big equations becomes really tedious or cumbersome. So there is an elegant way of writing this also. So that is being done using Einstein summation convention. So you write this sigma dash mn as it is nothing but writing sigma m dash n dash is nothing but sigma dash mn. I can write this is equal to AMI ANJ into sigma ij. So this is a compact way of representing all this transformation. So where, let's say, when I say ij varies from 1 to 2, so it represents 2D state. When I and j represent moves or changes from 1 to 3, it is a 3D state. So this is a very elegant way of representing this. So let's understand this, what exactly these conventions are. Let me give you an introduction to it. So these are called as tensor notations or Einstein summation convention. So in itself it's a very big thing. Here we will be dealing with its very brief introduction, which will be useful for our course. So there are different rules for this Einstein summation convention. The rule 1 is any index repeated twice in a single term is summed over. So it can sum over, let's say, till n times. So typically n equal to 3, we have seen it, I have mentioned in earlier slide. So n becomes 3 when we have 3D, when we are dealing with 3D structures or 3 dimensions. So here, let's take this same example. Sigma dash mn is equal to AMI ANJ sigma ij. Okay. So here in this case, what are the indices? So we here it means any index. Okay, so what are the indices here? Here you have m, n, I, and j. These are indices. Now, which is repeating twice in a single term? This is a single term. So which is repeating twice. So I, you can see here, I is repeating here, and I is also repeating here, and J and J. So I and J are repeating twice. So they must be summed over. Let's do that. So I and J is appearing twice, so they must be summed over here. Let's say I J equal to 1 or 2, they move from 1 and 2, and or takes the value of 1 and 2 for 2D case. So let's take first condition, J equal to J takes values of 1 and 2. Let's write this or expand this term. So you have sigma dash mn equal to AMI AN1 sigma I1 plus AMI AN2. Now here I am taking J equal to 2 and sigma I2. Now I take I from 1 to 2, so it becomes sigma dash mn. Now here I'll put I in both this term 1 and then again 2. So here it becomes am1 an1 sigma 1 1. Now in this term am1 an2 sigma 1 2. Now I'll sum it over again for 2. So am2 an1 sigma 2 1 sigma 2 1 am2 am2 an2 an2 sigma 2 2. So we can see that we summed over for j and I, and you can see that you have 4 these terms which was just compacted in as one term. So this is what is the Einstein summation convention. So what it says that if any index is repeated twice, it must be summed over. So we summed over for I and j because they were repeated twice. So summation can be done till what? Till you define I and j. Like for 2D, we define I and j varies from 1 and 2. So I and j are called as dummy index. So these are dummy index. So what does that mean? I can replace it with any index I want. Let's take an example and understand it. But there are conditions which you have to put. So they should not already be there in that expression. So that means they should not be present, and that is over the same range. So let's take an example. For example, I replace I by L. So L is not present already here in this term. So I can replace I by L. And also K is not present over here. So I can replace j by k. So this is what it means. They should not be already present in the expression. And now what are how the L and K should vary? They also should vary from 1 to 2. So they should have all the same range as that of I and J. So in principle, I can write, so this represents one and the same relation. AMI, ANJ, sigma ij is equal to AML, ANK, sigma LK. So what I did here is that I represented I by L and J by K. So now let's look at this term again, and here M and N are occurring only once. So they are called as free index, and the property of free index is that they can't be replaced with another indices. So you cannot replace M and N, unlike dummy indices, which we can replace with certain conditions. Rule number two for this Einstein summation convention, that no indices occur 3 or more times in a given term. So let's understand this also. So I have this given term AMII, ANJ, sigma ij, and I take another example. I have AMI, ANJ, sigma ij plus BMI, ANJ, sigma ij. So in first term, this I is occurring thrice. So this is not allowed according to rule number 2. Now in second case, how many times I is occurring? So here I have I 2 times and I 4 times. But this is not 4 times. So here it tells you that in a given term, so term is this term. So when I say a term, so this is one term and this is another term. So here I is 1, so it is only 2 here, and in this term it is I and I it is 2. So here I is occurring only twice. So writing this is right. So we are not breaking the rule number 2. Rule number 3. In equation involving Einstein notation, the free indices should match on both sides. So this is very straightforward. So I have free indices which occurs only once, isn't it? So xi here I is free indices, I is free index, I is free index, j is also free index. But here the free index are 2 and here free index is 1. So it is not matching. So this is wrong. Now xj is equal to aik plus uk. So you can see that the j is one free index, I is one free index, k is another free index. So here it is 2 and here it is 1, so it is not matching. So this is not the right way of writing equations using the Einstein notation. Now here xi is equal to aik plus uk. So here in this case xi, which is matching, so this free index 1 here, which is I, is also free index, which is I here. Here k is another free index, but it is matching. So here the free index I is matching with another free index I. So this is the right way of writing Einstein notation. So you can read about this Einstein summation convention, and let's look at its utility for understanding the transformation for stress state using direction cosines. So we have transform stress state using, these are direction cosines, and this is my given initial stress state in reference coordinate axis. So say here I and j are dummy index and they are occurring twice, so they must be summed over. So here I am summing it over from 1 to 2. So let me write it down. So I can write this term. So let's consider first I takes a value of 1 and then 2. Similarly, j takes value of 1 and then 2. So I can write as am1 an1 sigma 1 1 plus am1 an2 sigma 1 2 plus am2 an1 sigma 2 1 am2 sigma 2 2. So what I have done here is that we have put I equal to 1 and in first case, so here I is 1 and second case I is 2. So you can write we have written these four compacted terms in this one single just a one term. So now let's say m equal to 1 and n equal to 1. With this special case, what you end up with is sigma dash 1 1, which is nothing but sigma 1 dash 1 dash. Now I put m equal to 1 and n equal to 1. So you end up in writing this relation of sigma 1 dash 1 dash. Now I have this my matrix of direction cosines which has these values. We have found it out. I replace these values over here. Let's do that, and you find that you will end up in this relation which is sigma 1 1 cos square theta plus sigma 2 2 sine square theta plus 2 tau 1 2 sine theta cos theta. And this is what we have got using our in our previous approaches. So now you verify this for sigma 1 dash and 2 dash or sigma 2 dash 2 dash and see to yourself that whether you get the same relations what we have found for sigma 1 dash 2 dash and sigma 2 dash 2 dash. So this was the utility of Einstein notations. You can write all these big terms into using one compact term. So let's move on, and we have studied this now for 2D stress state. Now let's apply it on 3D stress state. So what we have done here, it is you have given a stress state in 3D. Now I transform it or do a rotation with theta, and I get some stress state in a rotated coordinate axis. I call it as A dash. I have this x1, x2, x3, and I just have this A dash in this oriented coordinate axis or rotated coordinate axis as x1 dash, x2 dash, and x3 dash. So we can use the same relation. A dash is equal to dA dt. Here you have to find out what are the matrix of direction cosines, and you know the stress tensor, and then take a transpose of matrix of direction cosine, and then you can get A dash. In tensorial notation, how you write it? That you write it in a similar fashion. That is sigma dash mn is equal to ami anj sigma ij. Now here, what's the change? Is that I and j varies from 1 to 3. So this is the only change. But this is what we have understood, that we can get these relations using just you can write this relation using just a compact form, which is called as tensor notation or Einstein summation notation, and you can get this A dash using this relation. So in case when nothing is specified, the indices vary from 1 to 3. This is a generally accepted thing. So if there is nothing is mentioned, if you have given this relation, so you can vary from I and j from 1 to 3.